Hey folks, welcome back. In this video we're going to go over question 2 from the 2018 SQA Advanced Higher Physics exam paper. So let's get going. Question 2 part A says a student places a radial controlled car on a horizontal circular track as shown in figure 2A. The car travels around the track with a constant speed of 3.5 meters per second. The track has a radius of 1.8 meters, and you can see that labelled in the diagram there. A part 1 says explain why the car is accelerating even though it is travelling at a constant speed, and this is worth 1 mark. Well, we can say it is constantly changing direction and therefore velocity, since velocity is a vector, meaning it consists of a magnitude and a direction. So for velocity to be constant, we would need the magnitude and the direction to be staying the same, but here the car is constantly changing direction even though the magnitude of the velocity, i.e. its speed, stays the same. And therefore acceleration must be non-zero as the velocity is changing. A part 2 says calculate the radial acceleration of the car, and this is worth 3 marks. Well, writing down what we know from the question, we're trying to find the radial acceleration. We know that the linear speed v is 3.5 meters per second and the radius r of the circular track is 1.8 meters. Writing down our equation for radial acceleration or centripetal acceleration, we have ar equals v squared over r. Substituting in the numbers gives 3.5 squared divided by 1.8, and if you put that into your calculator you should get an answer of 6.8 meters per second squared. A part 3 says the car has a mass of 0.431 kilograms. The student now increases the speed of the car to 5.5 meters per second. The total radial friction between the car and the track has a maximum value of 6.4 newtons. Show by calculation that the car cannot continue to travel in a circular path, and there's 3 marks available for this. Well, first we need to calculate the centripetal force required to keep the car moving in a circular path, and then compare this with the radial frictional force. So we're trying to find the centripetal force F. We know the mass m is 0.431 kilograms for the car. We know its linear speed v is 5.5 meters per second, and the radius of the path is 1.8 meters from earlier. So writing down our equation for centripetal force in terms of linear speed v, we have F equals mv squared over r. Substituting in the numbers gives 0.431 times 5.5 squared divided by 1.8, and if you put that into your calculator you should get an answer of 7.2 newtons. But we're not finished yet. We need to now compare this with the radial frictional force, which we're told up here. So we can say that since 7.2 newtons for the centripetal force is greater than the 6.4 newtons for the radial frictional force, then there is insufficient friction to keep the car on the track. So we would need the frictional force to be equal to 7.2 newtons or greater than 7.2 newtons in order to keep the car on the track. Part B says the car is now placed on a track which includes a raised section. This is shown in figure 2b. The raised section of the track can be considered as the arc of a circle which has radius r of 0.65 meters, and you can see that radius labelled there. B part 1 says the car will lose contact with the raised section of track if its speed is greater than Vmax. Show that Vmax is given by the relationship Vmax equals the square root of gr, where this is worth 2 marks. Well, we can say that for the car to stay on the track, the force due to gravity, i.e. the weight acting on the car at the top of the raised section, must be greater than or equal to the centripetal force needed to maintain circular motion. Or in other words, the centripetal force must be less than or equal to the car's weight. And that's because it's the weight of the car that's providing the centripetal force here. And we can say that maximum speed Vmax will therefore occur when Fc equals Fg, i.e. when the centripetal force is equal to the gravitational force, i.e. the weight. So that means we have 2 equations. Fc for centripetal force is equal to mvmax squared over r, and we have Fg equals mg, which is really just our weight equation, W equals mg, where we're using Fg to mean gravitational force because weight is the force due to gravity. So what we want to do is equate the 2 forces here, so we have mvmax squared over r equals mg, where we're just using Vmax because that's the maximum speed that we're trying to find. And you'll notice we've got mass m on both sides here, so we want to cancel the m's on both sides to get Vmax squared over r equals g. And now we want to rearrange for v squared or Vmax squared first of all. So doing that we can multiply both sides by r to get Vmax squared equals gr. And lastly we want to square root both sides, so we get Vmax is equal to the square root of gr. And that's what we were asked to show, remember. B part 2 says calculate the maximum speed Vmax at which the car can cross the raised section without losing contact with the track, and this is worth 2 marks. Well, here it wants us to use the equation that we've just derived, so even if you weren't able to do the previous part, you're still able to use the equation now that they've given you. So we're trying to find Vmax. We know that g, the gravitational field strength on Earth, is 9.8 newtons per kilogram, and we know that r, the radius here, is 0.65 meters. So writing down our equation that we were given, it's Vmax equals root gr. Substituting in the numbers gives root of 9.8 times 0.65, and if you put that into your calculator you should get an answer of 2.5 meters per second. Lastly, B part 3 says a second car with a smaller mass than the first car approaches the raised section at the same speed as calculated in B part 2, so that's the 2.5 meters per second. State whether the second car will lose contact with the track as it crosses the raised section. Justify your answer in terms of forces acting on the car, and there's 2 marks available for this. Well, we can say that a smaller mass means that the weight of the car is now smaller, and therefore a smaller centripetal force is needed to maintain circular motion. The second car will therefore not lose contact with the track. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.